The first car you ever bought, right? First truck, car, whatever.
Second was my first full truck.
Like real car?
It's a 72 F250.
Sounds cool. I don't really know what that means, but I mean it's a Ford, right?
Yeah.
That's what the F stands for. Anyways. All right, here we go. Go to page 643. All right, if you look, I talked about this last week. I don't like the example, but at least it gives you a visual here. So when you start with a reactant, cis-stil-ben, or bean, ben, you start with 0.850 of that reactant. As it reacts, breaks down, whatever it's doing, it has some sort of change in concentration. That little chart, it's called an ice table. We write ICE on the side of the paper, ICE, just like in the book. We're going to do a bunch of these. We use this for acid-base too, so it's good to learn right now. So anyways, there's some sort of change. What is that change? Well, you can figure it out with just some fairly simple algebra if you know the K value. So if you keep reading, it's minus X, meaning the reactant loses a certain concentration. The product gains that exact same amount. Right, conservation of X. Then the equilibrium concentration is you just using the variables in an equation essentially. So when you set up your K expression, products over reactants, you're going to have X by itself, because it's just one product, over the initial concentration minus the change, because that is the equilibrium concentration. So everything we've done so far, they gave us the concentrations at equilibrium. And they said, all right, solve for K, or solve for Kp. Or they gave us the K and the Kp, and they gave us equilibrium concentrations and said solve for one of the other ones, like the homework. So they kind of gave us a lot of information. Now, all they're going to give us is the initial and the K value, and they're going to ask for the equilibrium concentration. So that's all this is. When I say ice table, that's what it means. It just helps you kind of like visualize and set up the problem. All right, so we're just going to do, we got about 10 minutes here. We're going to do just a few of these, at least 2 of these, and then I'll give you some practice for homework. All right, so if you look at the very, not the very bottom, but above that checklist there, the 1, 2, 3, it gives you the answer. So the cis-stil-ben is 0.034 at equilibrium, and the trans is 0.816, which makes sense. You're going to have a lot more products than reactants because the K is so high, right? It's 24, so you're gonna, that change is gonna be significant enough to give that number above 0, right? So, so I'm just showing you this because that's where we're headed. That's what we're gonna do. Let's see. Did they give us a good sample problem here? Flip the page. Look at 644. Again, look at the solution. There's your ice table. This time you have 2 reactants and 1 product. They gave both initial concentrations of H2 and I2, 0.5 and 0.5, and you don't know the product yet because the initial, there is no product. The change, and here's why I'm showing you this, the change is a little different than the one on the other page. Because there's a 2 in front of HI, you have to double that X. So it's minus X because it's losing something when it reacts, and it's forming twice the products. That's what stoichiometry tells us. Now, if you set up your K expression, it's going to be 2x squared, because there's a 2 in front of HI, over 0.5 minus x times 0.5 minus x. Now, this is very typical on an AP test because there are problems with the quadratic equation, but we're not really going to mess with it, and AP is not going to make you do that either. So what you can do is you just take the square root of both sides, and that gets rid of the square, and it gets rid of one of those 0.5 minus x's on the bottom. Where we run into trouble is where you can't take the square root, then you're going to have to use the quadratic equation, which gets kind of crazy. I don't know if there's probably one in my notes that we could do, but I think in the past I kind of just skip over that because really that becomes a math problem. They want to know if you can do the chemistry, not necessarily the quadratic equation. But I'm just throwing that out there that does happen. So why am I showing you this? Again, another way to set it up, the ice table. The difference here is there's a coefficient of 2, so therefore 2x, and it's squared because there's a coefficient of 2. So these two just kind of help you set it up. You know what? Instead of doing the one I have in my notes, let's do that practice problem right there. 644, do that practice exercise at the bottom. Consider the example 14.9, starting with a concentration of 0.04 for HI, calculate the concentrations of all three. So use that exact same reaction. All right, this time they're giving you the concentration of HI, and they want to know what's the equilibrium of HI, H2, and I2. So the exact same reaction. Yeah. So there's kind of two ways you did they give us the K value? Yeah, it's 54.3. So you guys can do this, or so before you start doing anything, just look up here. If you want to flip this, if that for some reason makes more sense to you, and you want the X's here over on the product side, you could flip it, just take 1 over 54.3. Or just leave it. So set up your ICE table, ICE, plug in your concentrations that they give you. They only give us this one. And then set up your X's and then your equilibrium. So actually, before you solve it, I want you to set up your ICE table. I'm going to come around and see how you're doing. So just use the example above, see if you can do it. Just set up the problem, and then we'll go over that part. All right, so go ahead, feel free to talk to each other.
I'm using example 1410.
So the same one I just talked about, right above the solution there, you're using that exact same reaction. Except
but the
practice exercise gives you a different concentration.
Oh.
But it's it's this reaction. So everybody should write this in their notes. This is what you're doing.
Yeah.
It told you the K value is 54.3. So K, C, 54.3, I, C, E. So again, set up your ICE table, and that's it. Set up your ICE table, and I'm going to come around and see if you set it up right. Max, you seen anything like this before?
I didn't have that kind of
Oh, you did? Like this kind of stuff? Okay, good. So all you're doing is writing the initial concentrations, and they only give you one of them. So the other ones are zeros. The X's show the change. So reactants and products, one side is going to be minus X, and the other side is going to be positive. This one's a little bit bizarre because they're giving you the products initially. So if you don't have any reactants initially, then it can't possibly be losing concentration in the change grow, right? You can't take anything away from nothing, right? Maybe in some weird math class, but not here.
So wait. So with the 2HI, so you have to double the number and then would square it in the equation.
Right. And this gets confusing. I understand that because you're like, well, I'm already doubling it. Why am I squaring it, right?
Yeah.
Because forget the numbers. If you were going to write the K expression, it would be K equals HI squared over H2 times I2. So you have to square HI, and then whatever's in that parentheses or brackets for HI also has to be doubled because there's two of them.
Oh my.
So the concentration's doubled because there's two of them.
Yes.
Then you square it because that's what the equilibrium expressions tell you.
Okay.
So it's a change, it's a more significant, it's like a change of 4, right, factor 4, because it's squared. Which kind of relates all the way back to kinetics. If it's squared, then it's going to be a quadruple effect.
Oh.
All right, look up here. 0, 0. What is this, 0.04?
Yeah.
Okay. These can't possibly lose any concentration because there's none there, right? So this is kind of, I'll admit, not the best way to start this off because it's reverse of what most problems are. Most are like the one above, where they give you these and they don't give you this. But it really doesn't matter because it's a reversible reaction. So this must decrease in concentration. It must, because there's 0.04. This must gain concentration because it's starting at 0. You can't take anything away from 0. So this is going to react and create these two. I know it's a product, but remember, reversible, it doesn't technically matter. You can start with this, and then you'll go this way. All right. Now, questions on why I put the 2 here? Because there's 2 there. So whatever change happens here, it's going to be twice that change because there's a 2-to-1 ratio. Okay. So now my equilibrium is always going to be these 2 combined. So 0 plus x, 0 plus x. So really it's just x. This is 0.04 minus 2x. So again, once you figure out these 2, you just add them together and write them down here. Maybe add's not the right word. Combine them. 0.04 minus 2x. 0 plus x. All right. So now my k expression is 54.3 equals 0.04 minus 2x squared
When do you double the point?
over, hold on a second. You don't double the 0.04 because that is the concentration you started with. It's already a number. It's already doubled.
Okay.
So that's already given to you. This is the number we don't know, but you do have to double that.
Oh.
So if they give you an initial, you don't have to mess with it. They already gave you the number.
Okay.
Does that make
Yeah.
any sense?
Yeah.
Okay. So then, why are we squaring 0.04 or minus 2? Because the equilibrium expression here would be 54.3 HI squared over H2 times I2. So whatever's inside this parentheses or bracket, which is this, must be squared. All right. So really this is x squared. So then we just take the square root of both sides. So this is x squared. We square root this, that gets rid of the squares. Someone do that for me quick. 7.37 equals 0.04 minus 2x over x. Can you guys solve that? Did we all do it? If not, go ahead and do it quick. And then we can check our answer in the back. Because I didn't do this, I'm doing it with you here. What is this, 14.9? So x is going to be these 2, but you'd have to subtract.
26 heavy?
Why is he talking about Henny's?
If he sees a number. 426.
What's x?
427? 427, that's the number.
How much?
0.00.
Yes, 4.3 times 10 to the negative third. X is 4.3 times 10 to the negative third. So that's this and this. HI, you would have to multiply it by 2 and subtract from 0.04. So HI would be, HI is 0.031. 0.031.
Wait, how'd you get 0.0?
Take this number, multiply it by 2, subtract from 0.04. All right, so I'll see hopefully a lot of you after school. I'm going to text a couple of these for homework.
Do you have an extra copy of this, please, Brad? I just need the